There's a famous saying that goes something like, an idea not coupled with action becomes no bigger than the brain cell it occupies. As electrical engineering students here at ASU, we've learned a lot over the past few years, and we've been asked to put that knowledge and our skills to the test. We are Team 46, and our team consists of Nathan Arumugam, Nathan Cross, Caden McGuffey, Jerome Stradling, and myself, Justin Woods. Our project is a PCB readout system and user interface for a 64-channel biosensing chip. It was created by Professor Josh Hyatt and his team. The project aims to identify target molecules such as viruses and defects in DNA. It does this by isolating a strand of DNA and measuring the resistance of the strand to compare it to known values. This project aims to give the home consumer the ability to test from the comfort of their own home without the need for expensive lab equipment. Caden will give us a brief overview of our chosen components.
Hello, my name is Caden McGuffey, and I will be talking about the components we used for our PCB design. Our most important component for our PCB is our microcontroller. It's one of Texas Instruments MSP 430 class microcontrollers. It was chosen for a variety of reasons. Firstly, it has a built-in 12-bit ADC, which is essential for a high-precision readout from our sensing chip. It also includes an LCD display for reading out our output and is capable of delivering power to specific components. The microcontroller will be reading the voltage from our transimpedance amplifier, which is an ADL 5308. The ADL receives its input current value from our sensing chip, which has 32 available sensing channels to select from. Specific channels are selected from a cascaded number of 4-to-1 multiplexers. These 4-to-1 multiplexes selected are the TMUX 1109s. The TMUX was chosen due to its capability to both select a specific channel for sensing a value and simultaneously transmitting bias voltage to the specific sensing channel. The PCB footprint on the right of the slide was developed on KiCad, and this visual can show us the wiring between our components. Next, we will have Nathan talking about our firmware development.
There are three components to the development of the firmware that's been programmed onto the MSP430. First, the analog input is received from the amplifier and converted to digital to be stored in a variable on the MSP. Then, an input current is calculated from the logarithmic voltage at the amplifier output. As shown in the formula here, the logarithmic voltage minus 1.1 volts is directly proportional to the logarithm of the input current over a reference current, with a slope of 200 millivolts per decade. Reversing this formula returns the input current value, which is then displayed on the LCD display. Finally, the user interface contains button 1 to select the channel, and button 2 is pressed and held to display input current from the calculations. Now Jerome Stradling will demonstrate the user interface programmed on the MSP430.
I will demonstrate the user interface for our project. The entire UI will be done through an MSP430 microcontroller launchpad. When the board is booted up, we will see this opening message, as well as an instruction to use the built-in push buttons to select the channel that we want to view. When the channel is selected, signals are sent to the multiplexers to engage the corresponding channel. Also, when the desired channel is selected, the second push button can be engaged to view the data from the ADC.
Thank you, everyone. So we're pretty much done with the design. We have everything done. All we need to do is solder the components onto our printed circuit board we've created. In KiCad, everything's done and ready to be soldered on, and then once we do, we'll implement the firmware our team has developed, and then we will see the precision and power of Dr. Hyatt's biosensor chip. Thank you.